Dr. Ranjani Parthasarathi is a professor in Department of Computer Science and Engineering. Her area of specialization is in computer architecture and computer networking. She had guided more than 5 PhD students and currently guiding 5 PhD students. She had published paper in more than 50 national and international journals. She worked in many sponsored projects and she got IBM Faculty Award for 2008.
Welcome to the UGC lecture series in computer science. The topic that we are looking at is networks. The subtopic that we are looking at today will be the data link layer functions. The function of the data link layer basically is to make sense of the data. The physical layer, as we know, just transmits the signals, data converted into signals, and the function of the data link layer is to make sense of the data. So, to make sense of the data, there are 4 major functions which are done at the data link layer: framing, flow control, error control, and link access or media access. Of these, we will be looking at framing today. Before we look at framing, let us just take a look at where this layer 2 appears in the stack. So, if you look at the internet model, we know that you have the physical layer and the data link layer appearing right above that. If you look at the same thing from the point of view of the IEEE standard, you have the transmission medium, physical layer, and the data link layer functions are divided into 2 parts. One is the media access control and the logical link control. So, we will be, when you are looking at the data link layer, we will be looking at the function of both the logical link control as well as the media access control. So, let us look at the logical link control first. So, if you look at the logical link control and if you look at where physically this actually gets implemented, the link layer gets implemented in the adapter, also called as the NIC or the network interface card. For example, the Ethernet card or the 802.11 card. So, if you look at what is actually happening, you have the sending node on one side, receiving node on the other side. The sending node takes a datagram from a higher layer, converts that or encapsulates it into a frame and sends it over to the other side. Now, you have the link layer protocol which handles the transfer of frame from this side to the frame on the other side. The receiving node now takes this frame, decapsulates it and passes it on to the higher node. So, this is what is actually happening in a network, and this job of link layer and the physical layer is typically handled by the adapters or the network interface cards. Now, if you look at the actual functions, let us just take a brief look at the various functions that we have. The link layer functions, so on the sending side, if you look at what is happening, we saw that it is encapsulating the datagram in a frame. Second, in order to do error checking and flow checking for flow control, it will add some additional bits which are what we refer to as error checking bits, flow control bits and so on. Similarly, on the receiving side, what it would do is it will first look for errors, flow control, etc. Then it will extract the datagram and pass it on to the higher layer. So, these are 2 functions that take place at the sending side and the receiving side. Now, if you look at the services that you have the link layer, so as we said, framing and link access forms one of the primary services. So, what is happening here? You encapsulate the datagram into a frame, you add headers and trailers. Now, headers and trailers are added in order to make sure that the framing gets done properly, in order to make sure that your flow control mechanisms are built in and the error control mechanisms are built in. So, we look at what actually needs to go into the header and trailer when we look at the error control and flow control mechanisms. The second thing that we need to do is you need to access the channel if it is a shared medium. If it is not a shared medium, then this job of accessing the channel really does not arise, but typically most of the media tend to be a shared, in which case you need to also look at the accessing of the medium. Third thing that you need to do remember is when you are handling things at the link layer, to identify the source and the destination, we use physical addresses. The reason we are highlighting this word physical addresses is that physical addresses are different from the internet addresses or the network addresses that we normally use. So, we talk of physical address, for instance, if you are using the Ethernet network interface card, physical address here would refer to the MAC address or the Ethernet card address. So, those addresses will be used to identify the source and destination in the headers. So, this is what is getting done when you are doing the framing service. Next service that we look at is flow control. So, what is the job of flow control? To make sure the sender does not overwhelm the receiver. So, what do we mean by sender does not overwhelm the receiver? A fast sender should not send too much of data to a slow receiver. So, when a fast sender sends too much of data to a slow receiver and the receiver is not able to process the data, then we have a problem of data being lost. So, this needs to be taken care of. So, this is what we mean by flow control. Next thing that we need to look at is error detection. So, we know that errors will be caused by signal attenuation, noise, etc., and the receiver needs to detect this error, that is detect the presence of the errors, and it also needs to send information to the sender. Either it has to asking for retransmission or it may just drop a frame. There are 2 options available. That is, the receiver detects the presence of the error and either signals the sender for retransmission or just drops the frame. If it drops the frame, then it is up to the sender to identify that it has not yet got some information from the receiver, and then make sure that it retransmits the frame or does whatever correction mechanism is required. So error detection as such is something which needs to be done at the receiver. Another option that is available is error correction. Here what we do is the receiver not only identifies the error but also corrects the error without resorting to retransmission. This is an option that is available if you use certain types of codes when you are doing the transmission. So error detection or error correction. So if you do error detection, then you need to do some control so that retransmission will take place, or you do error correction, in which case the receiver itself identifies and corrects for the errors. So these are the primary functions that we need to look at. Of these we will be looking at framing, and in framing we need to also identify how the framing is done depending on whether we are doing synchronous transmissions or asynchronous transmissions. So which means we first need to identify what we mean by a synchronous or an asynchronous transmission. So let us look at what we mean by synchronous and asynchronous transmissions. Normally, with respect to synchronization, there exists a hierarchy of tasks that need to be done. That is, synchronization needs to be done at various levels. First is of course at the bit level. So what we mean by this, you need to recognize the start and end of each bit. So this is an important task. Typically this gets done at the physical layer. Next is character or byte level synchronization, which means you need to recognize the start and end of each character, or you can look at character as a small unit of data at a byte level. So you need to be able to recognize that you have a byte that you have received. So this is what we refer to as character or byte level synchronization. Third is you need to do a higher level of synchronization, that is you need to be able to identify that you have received a block, that is recognize the start and end of each large unit of data, blocks of data, and when we are talking about the data link layer we normally refer to these as frames. So you need to be able to identify beginning and ending of frame, right. So this is what we mean by synchronization tasks. So when we talk about synchronous versus asynchronous transmission, the difference comes as to at what level you are doing the synchronization. So let us look at asynchronous transmission first. In asynchronous transmission, we send one bit at the beginning and one or more bits at the end of each byte. That is, before you actually transmit a byte, you send what is called as the start bit, and similarly at the end of the byte you send what are called as stop bits. Now you could use just one start bit, or you could use one stop bit, or you could use more number of start bits or stop bits depending on what kind of scheme we use. Okay. So just for an example, I might use a 0 for a start bit and a 1 for a stop bit, or I may use a 1 for a start bit, 1 for a stop bit. The option is left to the designer, and there may also be gaps between each byte. Okay. So as you transmit a byte, then you may not transmit anything at all, then you will transmit another byte, but the beginning and end of each byte's transmission is identified by means of these start bits and the stop bits. So the assumption here is that the bits are still synchronized, that is we are talking about asynchronous at the byte level. Okay, asynchronous at the byte level is what we are talking about. That is, the bits are still synchronized and their durations are the same, and as I said, this is something that would be handled by the physical layer. So we are talking about adding some framing bits in order to make sure that asynchronously at the byte level you are sending data, but you are able to recognize the beginning and end of each byte. So let us look at how that gets done. If you look at how the framing gets done, so you can see that typically when the line is idle, let me assume that the line is high, and then before I start transmitting a byte of data, I add a start bit. Okay. So assuming here that the start bit is low, and I am also assuming that I am using a 1.5 bit time frame to indicate the start bit. So 3t by 2 is my start bit duration. Then it is followed by the data bits. The data bits might be 1 or 0 or whatever depending on what data needs to be transmitted. And then you have the stop bit, assuming here that the stop bit is a 1 bit duration. So you have a stop bit which is high. So if you look at, for every byte of data therefore that needs to be transmitted, you will add the start bit and you will add a stop bit. Example is data transmitted at random intervals. Typically, for example, in a keyboard, you just press keys at random in a keyboard, 1 byte of data gets transmitted. And if you look at the direction of transmission, starting from the start bit, data will get transmitted. So this is how the framing will get done in an asynchronous transmission. And the receiver will sample the data bits at the middle of each of these bits, so that it will be able to identify what the bits are, whether it is a 0 or a 1. So this is how the framing will get done if you are looking at asynchronous transmission. This is a very simple scheme. Again, this picture here will show you how there are gaps between different units. So look at what we have here. So this is the direction of data flow, this is the sender and this is the receiver. So let us say this is the data pattern that we are transmitting, say some byte pattern that you got. So I am adding a start bit let's say 1 is the start bit and 0 is the stop bit that's going to be added. So as I send data, you can see what's happening. So this is some data that's already been sent, right? So then you will have a gap between this the stop bit of one and the start bit of the other. This is the end of the previous frame, this is the beginning of the next one. So I have a start bit 0 followed by the actual byte that needs to be sent, then I have a stop bit. Then there is no data being sent, so there is a gap. So again you have, so which means the line would be idle. Again the beginning of a transmission, of beginning of a byte of data being transmitted would be identified by means of this start bit. Start bit, data bits, stop bit. Again a gap, start bit, data bits, stop bits, and so on. So this is how the data will flow in an asynchronous transmission. In synchronous transmission, let's look at what's going to happen. In synchronous transmission, the complete frame is transmitted as a contiguous string of bits, and the receiver endeavors to keep in synchronism with the incoming bit stream for the duration of the frame. That is, an entire frame of data consists of many number of bits, many number of bytes, is transmitted as a contiguous string. And it's up to the receiver to make sure that it identifies the duration of the frame and identifies that this is the beginning of the frame and this is the end of the frame. Okay, this is what happens in synchronous transmission. So let's look at some details of the synchronous transmission. So what we are talking about here is, and we can also see how it differs from asynchronous transmission, blocks of characters are transmitted without start and stop codes. So no start bits and stop bits for every byte that is transmitted. So naturally it means that it is faster in transmission, the overhead that you have is less. Okay, so second point to remember is the transmitted stream is suitably encoded so that the receiver can stay in sync. So now naturally in asynchronous transmission you had a start bit and a stop bit for every byte that was transmitted. So the presence of a start bit was used to synchronize the receiver on the other side. Now here there is no such synchronism available and a stream of bits are being sent. So when a stream of bits is being sent, you need to have a mechanism by which you make sure that the receiver will stay in sync with the transmitter. So how is that done? There are two methods which are available. You could use a separate clock line, which means that a separate clock signal is being sent and this clock signal is used to synchronize the receiver and the transmitter. Now this may work when you are having a transmission over very small lengths of a line. For instance, within a computer, if you are having data being transmitted from one end and received on the other, say for instance from one card to another card or from one chip to another chip, you could make use of something like using a separate clock line, but this does not work really well when looking at long distance transmissions. So in those cases what we do is you embed the clock information into data. That is, we have already looked at this when we looked at data link layer, when we looked at the physical layer, and we are looking when we do data encoding. So when you do the encoding, you make sure that you use things like biphase encoding, and in biphase encoding we have seen that you make sure that there are enough transitions in the signal so that the clock information is embedded in it. Once the clock information is embedded in it, you will be able to recover the clock at the receiver side and use that to synchronize with the transmitter. So this is something which is necessary when you do synchronous transmission. And when we do synchronous transmission, we have a mechanism to identify the frames in a synchronous transmission. That is, for every frame content, for the frame contents, you will have a preamble bit pattern that is added and a postamble bit pattern that is added, which helps to identify that this is the beginning of the frame and it is the end of the frame. The contents of each frame are encapsulated between a pair of reserved characters or bytes for frame synchronization. So this is how the frames will get identified in synchronous transmission. So we will look at how the preamble and postamble bit patterns are added after we take a break. Welcome back after the break. So we are talking about identifying frames in synchronous transmission. As I said, you have the frame contents, and to the frame contents we add some bit pattern at the beginning and some bit pattern at the end in order to identify that there is a frame. So this bit pattern added at the beginning is called as a preamble bit pattern, the one that is added at the end is called as a postamble bit pattern. So let us look at how this gets done. There are different mechanisms by which you can do this framing, so let us look at how that gets done. One of the first methods that we talk about is called as a sentinel based framing, in which some special characters are used at the beginning and at the end. Okay, so we say that you delineate a frame with special pattern of bytes or bits. So both are available. It could be a byte based framing or a bit based framing that we use. If you use a byte based framing, then we talk about using patterns like DLE STX or DLE ETX kind of patterns, which are used to identify the beginning of transmission and end of transmission. STX for instance stands for a start of transmission, ETX stands for end of transmission, DLE typically is a special character which is used, which actually expands to data link escape character, and is a special character which is used along with ETX in order to identify that you come to the end of the frame. Similarly, DLE followed by STX is treated as a pattern which identifies the beginning of a frame. If you are using a bit based sentinel, so then you could use a special pattern like something like 0 followed by 6 ones followed by a 0, what we refer to as a flag pattern, to identify the beginning of a frame or the end of the frame, or rather it is used for both beginning and the end of the frame. Use the same pattern, and you can have the frame contents being provided in between this flag pattern. So this is the start flag, this is the end flag. Okay, so you have the frame contents being provided within that. This is what you could do in a sentinel based scheme. Now one of the problems that you have in a sentinel based scheme is what will happen if the special patterns that we are talking about occur as part of the data itself. So look at what happens here. So I am talking about using 0 1 1 1 1 1 0 as a pattern which is going to identify that it is the start of a frame or an end of a frame. So the question is, what happens if this particular bit pattern appears somewhere in the data over here? Now if this pattern appears somewhere in the data here, then we have a problem, because that would now get interpreted as if it is the end of the frame itself. So now your frame would get truncated. So that is something that needs to be avoided. So what if special patterns occur in the data? How do we solve this problem? The solution that we use is referred to as bit stuffing or character stuffing. That is, when using a bit pattern, we use a scheme called bit stuffing, and when using a character based pattern, we use something called character stuffing. Now what does this bit stuffing or character stuffing actually mean? It is something very similar to using escape characters or escaping the special characters. It is very similar to escaping special characters that we use in C programs. So for instance, if you are using a printf and you had to printf a slash, you would say you would put a slash before that as an escape character, right? So it is something very similar to that. So let us look at how that gets done. So in character or byte stuffing, what we do is, with the sender will stuff an extra DLE into the data stream just before each occurrence of an accidental DLE in the data stream. That is, I am assuming that I have a DLE pattern appearing in the data stream. Now we know that DLE is a special character, but if it appears as part of the data stream, then you stuff, the sender will stuff an extra DLE before this DLE that is being sent, and the receiver side, the data link layer, will destuff the DLE, that is, it will remove this additional DLE before the data is given to the network layer. Okay. So this is what gets done. So let us look at how this is done. So for instance, the first picture here tells me what is the data that I actually need to transmit. So this is some transparent data, right? So you have a DLE STX added, DLE ETX added to indicate the start and the end of the frames. So now, so before data transmit, let us look at what is there inside the data. Inside the data, say I had some characters A, B, H, W, and I also had a DLE pattern appearing over here. Now if this DLE pattern appears, then naturally I need to look at how I can identify that this is not a special character, but it is just actually part of the data. So to do the bit stuffing, what you do is, you can look at this is your stuffed data. To do the character stuffing, you add another character, this DLE character, an additional character is added and sent. So what is actually sent from the sender would be this, the transmitter would send this data, that is DLE STX AB, and you have a DLE character. So there is another stuffed DLE character which is used over here, then followed by HW, DLE and STX. And at the receiver, you will unstuff this or destuff it. So what does that mean? I will remove this additional DLE. The moment it finds a DLE and finds another DLE following it, it removes one of the DLEs. So you know that this was a stuffed DLE character, and so it will be able to recover the actual data that was transmitted. This is what happens in byte stuffing. Let us look at bit stuffing. So here our assumption was each frame begins and ends with a special bit pattern called a flag pattern, which is 0 followed by 6 ones followed by 0, which is 7E in hex. Now in order to do bit stuffing, when do we need to do bit stuffing? It is when this particular pattern appears as part of the data. So what you do here is, the sender always inserts a 0 the moment it sees 5 ones, and the receiver always removes a 0 appearing after 5 ones. This is the idea that is used in bit stuffing. Let us understand this clearly. Okay. So what do we talk about here? We know that the moment 6 ones occurs, it is a flag pattern. So what the sender actually does is, it makes sure that whenever you have 6 ones appearing in the data, you make sure that you add a 0 as soon as you have seen 5 ones. So you make sure that never you will get a pattern of 6 ones appearing as part of the data. So this is the idea that is used in bit stuffing. Let us take an example. So let us say this is our input stream that you have. Okay, you can see that I have bit patterns here which have number of ones occurring together. Okay, so here there are only 2 ones, a 0, so there is no problem about that, but the next set of ones here, there are 1, 2, 3, 4, 5, 6, 7 ones are there in this pattern. So let us look at how this will get stuffed. If you looked at the stuffed stream, the moment it sees 5 ones, 1, 2, 3, 4, 5, it adds a 0 here, and then that is followed by the remaining 2 ones, then you have the remaining 2 zeros. Again, if you see here, there are 5 ones over here. So, the moment it sees these 5 ones, you have another stuffed bit 0 which is added. Next 0 followed by, if you look at this pattern here, there is a large stream of ones over here. That is, there are 10 ones which are available here. So, these 10 ones will actually get stuffed as, you will have 2 zeros that get stuffed there, one for each 5 bits that over here. So, 5 ones followed by a 0, another stuffed bit here, 5 ones followed by 0. The ones when 0, the zeros which are in red are the stuffed bits that have been added, and then followed by the next 5 zeros which are over here. Now, at the receiving end, look at what is happening. So, what is the receiver supposed to do? It is supposed to remove these stuffed zeros. Now, how does it identify these stuffed zeros? Whenever it finds a 0 after 5 ones, it will remove those stuffed zeros. So, you can look at the unstuffed stream. The unstuffed stream now, look at, you can see what will happen. It will see 5 ones followed by a 0. So, it will remove this. Then it gets 2 ones. So, you can see that the unstuffed stream now will get back the 7 ones that was transmitted together. 2 zeros. Again, if you look at this here, 5 ones followed by a 0. So, you drop this 0, so you get back your original pattern. Similarly here, these 2 zeros will be dropped because they follow 5 ones, and you will get back your 10 ones pattern together. So, this is what is done in bit stuffing. So, we are adding the zeros whenever we make sure that a pattern of 6 ones is likely to occur. So, even before the 6 ones pattern occurs, that is the moment 5 ones occurs, you add a 0 and remove it at the other end. So, using this bit stuffing mechanism, we avoid the problem of data being interpreted as a flag pattern. Okay. So, this is what happens in bit stuffing. So, to summarize that again, whenever the sender data link layer encounters 5 consecuting ones in the data stream, it automatically stuffs a 0 bit into the outgoing stream. And whenever the receiver sees 5 consecuting incoming ones followed by a 0 bit, it automatically destuffs the 0 bit before sending the data to the network layer. Okay. So, this is what happens in bit stuffing. So, this is a sentinel based framing that we looked at. Next thing we need to look at is a very simple scheme which is called as the counter based framing scheme. Here what you do is, to identify the end of the frame, we actually put a counter or a count of the amount of data that is actually being sent in the frame. That is, you include the length of the payload, include the payload length in the header instead of putting a sentinel at the end. So, for the beginning of a frame, we still need to have some special character that we will use, but the end of the frame will be identified by means of a byte counter or a byte count which is available as part of the header itself. Okay, let us look at how that gets done. So, let us say for instance, I have this particular frame of characters being sent. So, every frame is at the beginning of every frame, you have a byte count field or a character count field that is added. So, if suppose I have something like this, let me assume that this is the beginning of a frame. I have a value 5 written over here, which is followed by 5, which indicates that the number of bytes I have in this frame is 5. So, 5, so this is the first character, then I have 4 characters here, this indicates that there are 5 minus 1, 4 characters available as part of the data in this frame. So, now automatically this is the end of my first frame and the second frame will begin over here. So, the second frame again, the first byte here will indicate the number of bytes that are present in this frame. So, if I say 5 here, so then again the next 5 characters are identified as the second frame. Then I have a value 8 here which indicates that the next frame now has 8 characters in it. So, you count 8 characters and you go for that, you know that the third frame has been received, now you are ready to receive the fourth frame. So, you again look at the character here and then you go ahead and keep on receiving the frames. The problem that can occur in this kind of a mechanism is, what will happen if this particular byte count field or the character count field gets corrupted. So, look at what happens here. Suppose this was the frame that was transmitted, the one that is shown above, but what is received is something like this, that is, in the second frame the value 5 let us say got transmitted as a 7, some error occurred. So, 5 was interpreted as 7 at the receiver. Now, what will happen? The receiver now will identify the second frame as a frame which is 7 bytes long, which means it will read this as 7, 6, 7, 8, 9, 8, 0, which means it will have taken 2 frames, 2 bytes which actually are part of the third frame as part of this frame. So, now you have one here appearing as a character count of the next frame, so which means that you will have a wrong retrieval of frames at the receiver side. Okay. So, how do we solve this problem? So, the problem I said is the count field getting corrupted. So, what if the count field gets corrupted, which causes the receiver to think that the frame ends at a different place. So, the solution that we use is, actually this is a very nasty scheme to work with. So, the solution that we use is, you have to anyway catch this later when actually you do the error detection. So, error detection must be present in the frame if you want to catch these kind of errors. So, if you have error detection available, then you would have identified there is something wrong with this frame, and you wait for the next starting sentinel for the start of a new frame. So, this is how you can do things in the byte count based method. This is not a very popular method at all, it is not used very much. Typically, it is a sentinel based method that is used, or another method which we will look at next. Next method that is available for framing is what is referred to as a clock based framing. So, here what is done is every frame is kept as a fixed size frame. So, there is no ambiguity about start or end of each frame, okay, but of course, it could be wasteful sometimes. We will look at how this particular framing gets done. We will understand this framing scheme with an example, which is the SONET mechanism that is used. Now, SONET stands for Synchronous Optical Network, a framing scheme which is used in synchronous time division multiplexing schemes, which is used for transmitting optical data. If you look at how the framing gets done over here, each frame is a fixed size frame. Okay. In SONET, which is used in what are called as optical carrier systems, optical carrier 1 standard, what is happening is you have 810 bytes of data forming a single frame, and these 810 bytes of data are organized as 90 bytes per row and 9 rows. So, 90 into 9 you have 810 bytes of data. Of this, the first 3 columns are used for administration purposes, some overhead data used for administration purposes, one column is used for transmission overhead. So, which leaves you with user data of 86 into 9 or 774 octets or bytes which can be sent per frame. So, if you look at the SONET frames being sent, you will have something like frames going back to back, and 8000 frames are sent per second. So, if you look at the data rate that you get, the raw rate is 8000 frames per second, 9 rows, 90 columns. So, you have 9 into 90 into 8. So, you have about 51.84 megabits of data that is being sent per second. Okay. So, the synchronization here gets done by having a special pattern in one of these bytes over here. So, the receiver will keep looking for these byte patterns, and based on this it will identify that it has come to the beginning of the frame. So, it keeps looking for this particular pattern to appear every 8000 frames, right. So, every 8000 frames, or for every frame, for every 90 into 9, 810 bytes, it look for this particular pattern to appear, and when this pattern appears, it is able to identify that this particular framing has occurred. So, these are some of the data rates which are supported with the SONET. So, OC1 for instance supports, as we saw, 51.84 megabits per second, and the beauty of SONET is that you can combine multiple OC1 or 3 OC1 frames can be combined to get higher rates of data transmission. This is something that is used in SONETs. You could look at this when you are looking at the details of SONET. But from the purpose of framing, you can see how the framing gets done here. Just frames being sent back to back, and the clock signal is embedded as part of the data. That is, some transitions are available in the data which allow the clock to be recovered at the other side, and just frames are sent back to back. So, this is referred to as clock based framing. So, to conclude or to summarize, what we have looked at today is functions of data link layer, framing, and in framing we talked about asynchronous and synchronous framing, and in synchronous framing we talked about 3 methods: sentinel based or byte, which includes byte and bit stuffing to take care of some problems there, count based and clock based framing. So, these are the 3 framing mechanisms that we have looked at. We have a few questions. Let me read out the questions for you. What are the functions of the data link layer? It is a simple one. What does framing mean? What is the difference between synchronous and asynchronous transmission? What is the overhead in transmitting 100 bytes in synchronous transmission? Why do we need bit stuffing? Question number 6. Show how bit stuffing will be done for the bit sequence 0 0 0 1 1 1 1 1 1, that is 7 ones, followed by 3 zeros, followed by 5 ones, followed by 4 zeros. What kind of framing mechanism is used in SONET? What is the primary data rate supported by SONET? So, these are the questions that you could use to review your understanding of the concepts that we have learned today. Thank you.